Okay, so our next talk is going to be about the identification, the comparison, and eventually the circumvention of antivirus detection technique. Please give Arne and Alaeddine a warm round of applause.
Thank you. So I'm Arne, and next to me is my fellow researcher Alaeddine, and today, as mentioned by Peter, we're going to introduce you a tool, a packer, that we developed to investigate identification of detection techniques of current antivirus products. So briefly, the agenda for today. First, I will introduce the term packing. Anyone in the room who has never heard of packing before? Okay, we have one, but it's a colleague of mine, so I don't believe him. So hereafter, we will be discussing the three main detection techniques that we have identified, which are static detection, code emulation, and dynamic antivirus detection. So who are we? We are both security consultants working for these respective companies, and we mainly conduct penetration tests. So packing is actually, a packer actually transforms an executable into another executable with the same or even enhanced functionality, but a different file system footprint. So a good example of a packer, before I start with that, what happens is the packer makes static changes to the file, and in order to reverse the changes that have been made in a static fashion, it will also inject a piece of code, usually called a stub, which will be executed firstly, and it will reverse the static changes made at runtime. So we have two main categories of existing packers today. First category is a compressor. Compressor is aiming to reduce the size of an executable. So it will run a compression algorithm on parts of the data of the input executable. And it will also inject the stub, which will do the decompression at runtime. The most famous example is UBX, which is, I think, known by some of you. A second example of a packer category is an obfuscator or a protector. And these packers aim at making reverse engineering of executables more difficult. So before being packed, in this example, before being packed, the executable can be debugged by immunity debugger in this case. But after being packed, the packer will inject some code or make some modifications that will crash the debugger. In this case, I found this one myself. If you put enough dots in your file name, immunity debugger will crash. So if anyone feels like playing around with it, go ahead. So it's obvious why a packer could be useful to evade static antivirus detection, because we all know that antiviruses use file signatures, or at least signatures based on malware they have discovered or seen in the wild. So if our packer can encrypt or modify the data, the signature that is in the malware, obviously we could bypass the signature detection of antiviruses in this manner. So in order to understand how a packer can be made, we must investigate the file format of an executable, the portable executable file format, which is made by Windows, obviously. So as usual with file format, we have a header and a data blob right behind it. So the header contains a lot of fields, two of which are really interesting and useful for a packer. First of all, we have the address of entry point, which is actually a pointer into the data section where execution will be started. So we use this to hijack the execution flow in order to execute our stub first. Second of all, the header also contains a section table, and the section table actually logically divides the data blob into sections. So, brief example, if we have a simple message box hello world program here in C++, and after compilation with Visual Studio, this is the section table that comes out of it. So first of all, the first section here is a .text section, and it actually contains the your code, the code that has been written. So in our case, the message box call. Important to note is the fact that this first section has some kind of characteristics, and this is actually a D word, but it means that this section is executable but not writable. So actually every section has some permissions in memory. Next, we have the RData section, or commonly called also the imports section. And this is actually a section which contains a list of Windows APIs that are required by the executable. So in this case, this is the message box function. What will happen is, at loading time, so when double-clicking the executable, the Windows operating system will load this executable in memory, and it will loop through the list of functions in the imports table structure, and it will load the necessary DLL, so in this case user32.dll, where the message box function resides. It will also locate the address of the message box function in memory, and it will hot patch this address in this section. So at runtime, this section will contain the correct addresses provided by the Windows operating system loader. Hereafter, we have the data section, which contains static data of our program. In this case, the hello and the world string. Hereafter, we also have a resource section. This actually contains, like the icon you see in Explorer of your file. This is stored in there. Also the version information when you look at the properties of a file, when it's been compiled, and what the developer was. This is all stored in there. And last but not least, we have a relocation table. This section, a relocation section, which also contains a table, a relocation table. And this is actually made by the compiler if you request it to compile with ASLR enabled. So only when you enable ASLR, this will be present. And again, the Windows operating system loader will use the structure present in this section table on the file on disk at loading time to be able to relocate the executable in memory. Because by default, all these sections are loaded at the image base address and then added to the virtual address. But with ASLR enabled, you must be able to relocate it in memory. So that's what this section is for. So there are a couple of requirements or enforcements that this section table makes, which makes making a packer more difficult. First of all, you have the imports table, the resource section, and the relocation section. These cannot be encrypted because the Windows operating system, it needs to be able to read these in clear text when loading the executable. For obvious reasons, because, for example, the resource section, it contains the icon, so if showing up in Explorer and it does not find an icon, it will immediately look suspicious. For the other two also, it needs to parse the imports table and the relocation table before execution is actually handed over to the file in memory. So for this reason, it is impossible to just encrypt these sections. Another enforcement is that the code section, it contains absolute references to the imports section and the data section. So a quick example here, the call to the message box function in the code section is actually using a pointer in the imports table, which contains at loading time the address of the message box function. So remember, this is not present on disk in this section, but it is provided by the Windows operating system when loading. So it's important to remind ourselves that these three sections cannot be moved, or for example, you cannot just simply expand the code section because you would push down the address of the imports table and the data section, and your executable will break. More specifically, this call will not be successful anymore. Okay, so now we know the enforcements that the file protocol gives us. We can now start tackling the two main challenges. The first challenge of making a good packer is that you need an extensible stub. The stub is the piece of code that you inject into the file that has to reverse the changes that the packer made statically. So as we all know, the code section contains assembly code because it's compiled. So our stub must also contain assembly code, and assembly depends on the architecture of the system. So in this case, our stub must contain architecture-specific code. Moreover, also our stub can to remain as generic as possible, we wanted our stub to be injectable anywhere in the process, not just at a certain location. So we must maintain position-independent code. And last but not least, we can also not rely on the Windows operating system to, for example, fetch us the addresses of Windows API functions. So we must do that ourselves through self-dependency resolution. So what we did is, okay, we first looked at the competition. So we went to look how UPX does it. And UPX actually, their stub are actually real assembly code. So for 32-bit, 64-bit, and ARM, they actually implemented assembly code in order to load the file, decompress the file in memory, and then jump to it. But since we are no assembly gurus, we took another approach. We used the Reflective DLL project of Stephen Fewer. Anyone in the room who knows Reflective DLL project? Okay, again, my colleague, thanks. Well, the Reflective DLL project is an open source project which is available on GitHub, made by Stephen Fewer. And it's actually a Visual Studio project, a DLL project. So it's a DLL which contains two main functions. First of all, we have the DLL main function. It's actually an empty function which tries to resemble the normal DLL main function of a normal DLL, right? But it's empty and it's for us to implement. So this is actually where we implement our stub code, like in our case, the decryption algorithms and stuff like that. Additionally, we have another function that is provided to us by this project, which is called the Reflective DLL Loader. And what this function will do is, will be explained in the next slide. So basically what we do first is we write our stub in the DLL main function. We compile it because it's a DLL project that is compilable. We compile it, and the first advantage becomes clear. We can compile it for different architectures. So we can write our stub in C and C++ with Windows API support, and we can then compile it to a low-level assembly block of code. Hereafter, what the packer will do is it will take the initial executable, it will use this complete DLL as a stub, it will inject this into the executable, and it will hijack the address, the entry point. So here you see the original entry point, and we hijack it to point to the loader. Okay, remember this loader function is provided to us. And what will happen when we start executing the file is, okay, the loader will start executing the file, and it will relocate first. It will relocate our complete stub, like the DLL, into the heap. It will not only do that, but it will also parse through our imports table, because we are a DLL, and DLLs also have an import table. It will parse through our import table and fetch the Windows API addresses, hot patch them where they need to be, and then it will hand over execution to our stub, which is the DLL main function. So at this moment, we are executing our original C++ code with full Windows API support, which is actually, we get for free by the Reflective DLL project. So we consider this as the first stage, and now we can actually start executing our packer code. So what we will do now is we will restore the original executable's memory layout, because remember from the last slide, we are actually making a copy here, so we have to remove ourselves again, and restore other modifications we've made, which will become more clear in a few slides, and then hand over execution to the original entry point. So we're actually restoring the original executable in memory and then handing over execution. Okay, so we tackled the first challenge by using the Reflective DLL project. That was for free, let's say. The second challenge was a bit more difficult. We have now a good extensible stub that we can compile for multiple architectures, but we still need to inject this stub in a stealthy manner, because antivirus products are also aware that packers are being used to circumvent detection. So what antivirus solutions do is really try to detect modifications to an executable file in order to see, okay, a packer has been playing with this. This is at least suspicious. So we will focus more and do more analysis. So again, we looked at the competition and we looked how UPX does it. So at the top, we have our Hello World example again, our compiled Hello World examples section table. And you see here the characteristics, for example, of the first section, our code section. You can see it's executable, it's readable, but it's not writable. When we look at the sections of the packed executable with UPX, we see that the sections have completely changed. You have UPX0, UPX1, and still a resource section. But of course, our point is this is really detectable. An antivirus can quickly look to the section table and see, okay, this executable is not compiled by a normal compiler. It will, when an executable is compiled by a normal compiler, it will, by Visual Studio at least, it will always look like this. If you use another compiler, it will still have a predefined layout. But this is really specific to a packer. So this is really trivial for an antivirus to detect. So we looked at a couple of other packers to see how they deal with this, but we haven't been able to find any packer that really attempts to remain stealthy. So if you see, these are all section tables of packed Hello World examples. You have a couple of packers who even deliberately, I think, add sections with cryptic names. You have some which double the amount of sections, but we have not seen one that really maintains the number of sections and tries at least to be stealthy. So we developed our own technique. First of all, we developed a rather simple technique called the inline technique, which is where we take the input executable, we encrypt its code and data section, so this is the output file, and we append our stub to the end of the file. Remember, we cannot squeeze our stub into between one of these sections because we cannot split them up because we would break the references from the code to the data and the import section. So we decided, okay, as a simple measure, we'll just append our stub as a last section, and we will hijack the entry point of the original executable, and we'll point it to our stub. So if you look at the section table, the change is rather obvious. You see that there has been a new stub section appended. And if we load this packed file with this inline technique into Olly debugger, it will immediately see that there's something suspicious. Namely, it will see that the entry point of this executable is not in the first section, not in the code section, but Test. Okay, I'm back. Oh, I'm back. Okay, thanks. I'll try to look out, but... So what I was saying is Olly debugger immediately sees that there's something suspicious about this file, namely that the entry point is not pointing to the first section, but to the last one. So entry point is outside the code, since the first section always contains the code in a normal executable. So we went ahead and we gathered some malware samples for both 32-bit, 64-bit, and we packed them with this technique. What we see is for 64-bit, it's already quite a good result. We only have 2 antiviruses who still detect a part of the original malwares. For 64-bit, that is. For 32-bit, it's a different story. You have a couple of antiviruses which still detect a high number of the malwares that were packed with this technique. You even have one antivirus which is actually detecting our inline technique rather than the original malware. So what we did is we took 110 samples. We first scanned them with all those antiviruses. Kihu detected 100. And then we packed the 110 samples, and we again scanned these packed files. And suddenly, Kihu started to detect them all. So actually, it's detecting our packing technique rather than the original malware. You also have some who are only detecting a smaller number of malware. And we believe we can divide the reasons in 2. So this part of the antiviruses, which have really a high detection rate still, we believe they are detecting the fact that the stub is added as a new section at the end, and the entry point is changed. What we expect this group, we expect that this group is actually detecting the malware for which they have a signature which is in another section than the code or data section. Remember from the slides, we are only encrypting the code and data section. The other three, we are not encrypting them because from the enforcement that I've mentioned, these must contain clear text valid data before runtime. And of course, if an antivirus solution decided to extract a signature from one of these sections, usually the resource section, it will still detect the malware. So, okay, we went ahead and we developed a new technique. This time our input is not only a malware, but it's also a template executable. Template executable is just a legitimate executable, for example, a Windows file or a popular third-party program executable. And what this technique does, it takes notions of both files to construct a completely new file, a new PE file. So what we do is we construct a new PE header based on both PE headers of the input. In our code section, we put all the sections of our malware encrypted, as you can see here. Plus we append our stub to it, and this will make up for our code section. So actually our code section will contain a piece of code and a lot of encrypted data. Hereafter, we append some of the legitimate sections of our template executable in order to let the final executable look legitimate. But actually, this contains data from a legitimate file, and we are not interested in it. We just want to look legitimate. Okay, this changes a number of things for our stub. It will have to do more work. In the inline technique, the stub just needed to decrypt these two sections and jump to it. Now it will have to decrypt the 5 sections, but it will also have to take over part of the work that normally is done by the Windows operating system, namely parsing the relocation table and relocating if necessary, and also parsing the imports table, fetching the Windows API, required Windows API function addresses, and hot patching them in this section in memory. But okay, this is rather similar to what the reflective DLL, reflective loader from the reflective DLL project does. So we managed to take over some parts of this code and managed to make this work. If we look at the changes to the original section table of our malware or of a Hello World and the packed version, we see that the main difference is that the code section has dramatically increased the size of the code section. Because, of course, it does not only contain our stub, but the complete malware, the complete sections of the malware in encrypted fashion. And if we load this packed Hello World in our Oli debugger, it still complains. And what it says is, okay, the code section, as we see it here, it is either compressed, encrypted, or contains large amount of embedded data. What Oli debugger tries to do when loading an executable, it will try to disassemble all the instructions, all the assembly instructions in your code section. But of course, in our case, it mainly contains embedded data, encrypted data, sorry. So it will not be able to properly disassemble all these bytes. And this is why we get the pop-up. But okay, we went ahead and we tested again our packed malwares against antiviruses. And we noticed that for 64-bit, we have no bars anymore. So 64-bit, at this point, we can bypass all static detection, all signature-based detection. For 32-bit, we still have 3 antivirus solutions which are detecting minor parts of the malware set that we initially used. So we have 2 possible explanations for this. First one being the fact that the same fact that Oli debugger is detecting, the fact that the code section, its entropy is not what it should be in a legitimate file. Second one is that we are constructing a completely new executable, and we are combining the original 2 PE headers of both our malware and our template exe into a new PE header. So for example, PE header contains the architecture of your file. So we take this one from the malware, because otherwise the malware would not run. But it also contains a timestamp, and we will definitely not take that from our malware because it might be suspicious. So we take that from our legitimate file. But of course, maybe there are some discrepancies in combining these 2 headers. So this could also be possibly used as a detection vector. This is at least what we figured out. So last but not least, we developed a new technique, which is called the resource packer. And in this technique, we work with the same two input files, which is a template exe and a malware. And what we do now is we just take the template exe, we write over parts of the code with our stub. So we hot patch our stub into this code section, and we change the original entry point of the template file to our stub, but it's still pointing to code, so we don't trigger that heuristics anymore. And what we do is we take the complete malware, including the header, we encrypt it, and we append it as a resource to our template file. So in the resource section, there can be a lot of things like pictures of your executable, like icons, stuff like that. So it's not unusual that a data blob is in there, which is not the case for the code section, which triggered the heuristics of the new PE technique. So, of course, our stub needs to do a bit more work now. It will first relocate to the heap. It will then decrypt the original malware, which is in the resource section. And last but not least, it will write this to the correct place in memory, to the expected place where this malware was going to execute, which is the beginning of the image base address, let's put it like that. And of course, it will still need to parse, like hot patch the import table, parse the import table, hot patch the Windows API address functions. Okay, so if you look at it from a sections tables perspective, we see that this is our template file, for example, mstsc, the remote desktop executable. And what we see is the only change is that our resource section has grown a bit. But apart from that, there's no change in the section table. Under the hood, we also override part of the text of the code section with our stub, but we just override parts. We don't increase the size of this section, so this is not visible in our section table. So actually, we just have a legitimate file with an extra resource and a piece of code hot patched in the code section. And finally, we reached the figure without bars. So this technique is able to circumvent all static detection of antivirus products. What I did not tell you in the beginning is the fact that for these experiments with the graphs, we used a stub that immediately calls exit process instead of properly decrypting the original sections and then jumping to it in order to isolate the static detection. We really wanted to see what an antivirus can detect just by looking at the raw bytes on disk. So we have a small demo here. Our packer is actually just a console process, and here we will use as an input file meterpreter, bind TCP, which is known by some of us at least, I believe, encryption XOR. No, okay, I'll just let it run. And we will pack this malware, the meterpreter, with our three techniques now. So first, for the inline, we don't need to use any template file, any legitimate file. But for the new PE and the resource technique, what we are using now is the Notepad++ as a legitimate file. Okay. So in order to prove they are still working, we execute them. And we can see that it's still asking for permissions to open up a port. So they are properly executing the packing techniques work. What you can also see is that for the inline, the file size is not really close to either the malware or the template file. For new PE, neither, but for resource, it is, because the resource file is actually just a little bit bigger than the Notepad++ template file. It's just added with the size of the malware, because we add the malware as an encrypted resource. Okay. So we transferred these packed files to a system which has McAfee antivirus on it. And when we do an on-demand scan of all these malware files, we see that none of them are detected in a static fashion. So actually what McAfee is completely bypassed by all these three techniques, which we will prove by also executing the malware packed with the inline packer. So actually the meterpreter will bind to port 4444, the classic port. And what we'll do now is we execute the inline executable, being our malware. And if we then we see that the port has been opened. So the malware is properly executing. And this was the same for the other two. So we did the same for Security Essentials from Microsoft. And yeah, we copied the files to this folder, in a shared folder. And actually, it immediately detected some of the files. So without even opening them, trying to launch them, not even starting an on-demand scan, it is immediately detecting these files. It's a bit slow, but actually, at the end, all of our 3 packed samples will be detected, which is remarkable because, especially for our resource technique, we can see, we are sure that not a single byte of the original malware is in the final executable. It is all encrypted in the resource section. So this is the moment when we figured out that they are playing with us and they are using another static detection technique, which is called code emulation. And Alaeddine will tell you all about it now. Thank you.
Okay, well, hi everyone. I'm really excited to be among you here today. Okay, so as Arne has explained, using the different packing techniques, it's possible to evade more and more antiviruses, which are using static analysis, until we use the resource packer, which are allowing us to completely bypass static analysis, because it has completely changed the initial executable, and it is also able to produce a final executable that is very similar to what we would expect from a standard compiler. The problem, however, is that there are some antiviruses which are still able to accurately identify the initial malware using a detection method, which is code emulation. So the natural question is, how are antiviruses implementing code emulation, and is it possible to bypass, and hopefully bypass it also in a generic way? Well, the way antiviruses implement emulation is that they are emulating a full Windows environment. And this way, they can execute our packed malware inside this environment, trigger the unpacking in memory, and then do further analysis on it afterward, either statistical analysis, heuristical analysis, or any sort of analysis that you find that they're commercial brochures that makes coffee, order pizza, and kick the ass of all the expendable guys. The problem, however, is that emulation needs to deal with a lot of challenges. The first one is the detection of packers or cryptors, or to be more accurate, is actually identifying at exactly what moment did the unpacking has finished. And this is very critical because analysis is very resource intensive, and it needs to be done at the exact moment. And if it is done prematurely, it will not analyze the unpacked malware, and this way it will miss it. The second issue, which is performance. I don't know if you've ever run Windows 7 on QEMU. It takes a lot of time. And antiviruses need to have as less of an impact on the user experience, and they need to execute the packet malware as quick as possible to be able to identify it as malicious or not. The third issue is bypass of anti-emulation. This is something I'll be talking extensively about, but basically it's the fact that we are able to identify emulation and we are able trying to bypass it. And this is something that we definitely see more and more use of it. There are already occurrences of it being used in the wild by malware. And finally, there is the issue of complexity. Implementing emulation for x86 or x64 architecture is really complex. And if you add to that the fact that you'd like to emulate a Windows environment with its different flavors, you add a significant layer of complexity. And if you add to that all these blocks that will handle identification of packers, that will try to enhance performance, and that will try to bypass anti-emulation, you add a lot of layers or more layers of complexity. In this way, you end up with a huge steam engine, which is definitely a marvelous piece of engineering, but also a very complex system. And it is actually emulation, which is the Achilles heel of emulation, which I'll show you afterward. However, it is very interesting to see how are antiviruses trying to tackle these issues, how they are trying to solve some of these issues. And actually, as weird as it may come, a lot of the technology that is being used by antiviruses is detailed in a lot of the patents. And this is just an example of Kaspersky, and this is a list of some of the patents that discusses the use of emulation to bypass, the use of emulation to detect malware. And they do it for obvious commercial reasons. However, from an attacker perspective, once you know how a heuristic is working, it's more or less straightforward to be able to try to bypass it. And it's also very interesting because actually a lot of the limitations, you don't even need to try to think about how you bypass it. The limitation are actually written black and white inside these patents, and you only need to re-implement them. So let's see how they're trying to solve some of the issues. So the first problem that we talked about is the identification of packers or cryptors, or as I said, is being able to identify at exactly what moment unpacking has finished. And to see how they are doing, let's take an example. So we have a packet malware for which this is the memory layout, okay? So we have the stop section, which is the code section that will start decoding the malware. We have our malware, which is encoded somewhere in memory, maybe in the .data section, maybe a resource, an entry in the resource section. And we have a newly allocated memory, which will host our decoded malware. So what will basically happen in a simplistic example is that the stop will start execution, it will start decoding the encoded malware, write it to this newly allocated memory, and then handle execution to the malware. So what does that mean is that we have this memory region which is both writable and executable. And this is very important because this is not something so common. With memory protections like DEP, like data execution prevention, memory is usually either writable or executable. There are legitimate exceptions for this. For instance, applications that use JIT, just-in-time compilation, use writable and executable memory. For instance, there is a lot of JavaScript frameworks that use JIT for performance enhancement. And for instance, there was actually a vulnerability that existed on the iOS JavaScript framework that uses the fact that we have a memory which is both writable and executable to execute non-signed code. Well, let's get back to our packer. So we have a memory page, which is both writable and executable. And this is an indication that unpacking has finished, and now we're starting to execute the malware. Well, this is used actually by some automated unpacking approaches. And the way this is done is that it works on two runs. There is the first run, where it is actually stripping all the writable flag from all memory pages, either existing memory pages or newly allocated memory page. And this time, every time it is writing to one of these memory pages, this will trigger an exception. And this way, we're able to track writable memory page. And then it will handle the exception, correct the memory page, and then continue execution until it's able to track all memory pages which are writable. And then it is doing second run, and this time it is stripping the executable flag from these memory pages that we tracked as writable. And what happens is that once it will start executing this memory page, which means the malware has unpacked and now it has started execution, again, it will trigger an exception, and we're able this way to identify that the malware resides in memory, and we can even use it to retrieve the original entry point because we are retrieving it with the exception. The problem with this approach is that imagine we have a malware which is packed with different packers, and this is a very plausible scenario. What happens is that if we apply this heuristic, these scanning need to be happen after each unpacking. And this is problematic because some antiviruses might drop the analysis after the initial scan, and this way it will miss the malware and will not be able to identify it. Well, for that, there is actually a better approach called Omni-Unpack. What Omni-Unpack does is that in addition to the fact that we have a memory which is both writable and executable, there is a second heuristic which is used, which is the call to dangerous EPA functions. And the logic behind it is that if there is a call to one of these functions, this could only come from the malware, meaning the malware has started execution, meaning the malware is now in memory, and now we can do scanning. However, I think that some of you, once we know how a heuristic is working, some of you could guess how we try to bypass it. And the way we could do that is by simply fakely unpack memory. We will allocate memory, which is writable and executable, and it will, for instance, unpack some shellcode that will call one of these heuristically dangerous functions. And if the analysis was ever to be performed, it will be performed during one of these initial fake unpacking, and it will miss the original malware. So this is how for the first issue is tackled by some antiviruses. How about the other issues, which is performance and bypassing of anti-emulation? And here I'm going to speak about the Kaspersky case because it's one of the most interesting. I believe, in my opinion, it's one of the most innovative emulator implementations. And to show some of the features that it has, we have a simplistic graph. So we have the emulator, which is executing a certain executable, which is a set of instructions. Then they go to the analyzer. Well, the Kaspersky emulator is separating emulation into two kinds of emulators. There is one which is in charge of system call emulation, and a second one which is in charge of standard emulation. And this is logical because they both have different logic, and by separating them we can apply different optimizations, as you'll see. There is actually one interesting feature that the Kaspersky emulator is implementing, which is caching of native code. And what basically it is doing is that, imagine we have a malware which is packed with UPX, which is an open source packer that Arne has already mentioned. Well, if the antivirus identifies that this sequence matches the decoding sequence of UPX. Instead of emulating these instructions, which might be 20 times slower, it actually will instead execute the decoding sequence that exists inside the antivirus. And this way, it will benefit from real hardware speed to be able to unpack the malware. And this is actually used not only as a performance enhancer, this is also used to bypass anti-emulation checks. And the way it is doing that is that imagine we have some anti-emulation check that is being executed before. Because because it has identified that this is the decoding sequence, what will happen is that instead of executing the check, it's able to directly execute the decoding sequence that exists inside the antivirus and bypass any anti-emulation check that exists. And this way it's able to retrieve the initial malware and do analysis on it afterwards. Another very interesting feature that the Kaspersky emulator is using is hardware acceleration. What basically it is doing is that it's allocating real memory and using real CPU to execute these standard instructions. And because it's simply instruction and not any EPA functions, there is less risk. However, it has a lot of limitations because we don't want to have any side effect that we would be jumping outside from the antivirus emulator to the real environment. So this is, as you see, there is actually a lot of features and a lot of complexity that exist inside an example, which is the Kaspersky emulator. And it is actually this complexity that is used, among others, to implement anti-emulation checks. And what anti-emulation checks basically are, they're simply trying to identify discrepancy that exists between the real environment and the emulated environment. And by having these discrepancies, they're able to come up with checks that have different behavior inside the emulated environment and inside the real environment. And this way, when we are doing when they are analyzing the packet malware, it will identify that we are inside an emulated environment, decide on not doing the unpacking, or simply take another execution path. Well, to identify these discrepancies, we work on 4 categories. There are definitely more, but these are the ones that we had the time to work on. And the goal is actually to evaluate the robustness of the different antivirus implementations. So the first one, which is related to time and anomaly. Second, which is interaction with file system, interaction with the network, and finally binary instrumentations. Right here, I'm going to just show you some examples of some of these checks and actually show you the evolution of some of these checks. So let's start with the first one, which is time and anomaly. Well, this is actually a check that has already been documented as being used in the wild. And the principle is, because antiviruses cannot keep analyzing the malware indefinitely, what malware authors will do is that they will try to stall this analysis by simply delaying the unpacking. And in this example, it's simply doing it by using a simple big sleep. However, this example doesn't work against some emulator implementations because they understood this anti-emulation check and they're able to bypass it by emulating the sleep function so that it would do sleep 1 or simply do nothing. So again, malware authors adapted, and they are actually trying to even use this fact that we have the sleep function, which is behaving differently inside the emulated environment, to be able to identify that we are inside an emulated environment. And the way they would do that is that they would use other EPA functions, and in this example, they're using the get tick count, which is executed before and after the sleep function to see if the sleep function is working correctly. The problem, again, is that this check doesn't work against some emulated implementation, because now they are emulating both the get tick count function and the sleep function to be able to make this check work. So in the same spirit, we try to have other checks that would allow us to identify this behavior, but without using any EPA functions. Because if we're not using any EPA functions, they cannot emulate it and potentially will make it harder for them to bypass. And the check that we came up with is the check that uses 2 threads. There is one thread, which is the counter thread, and a second thread, which is the watcher thread. What the counter thread is doing, it is incrementing a shared variable separated by multiple sleeps. And the watcher thread is basically a big sleep that will compare the counter variable with the expected value. And in this example, it is equal to 10. And this is what we would see inside a real environment. Okay? However, inside an emulated environment, where the sleep function has been reduced to sleep 1, or simply doing nothing, what will happen is that the watcher thread will stop execution very early. And when it will try to compare the counter variable with the expected value, it will not match, hence allowing us to identify that we are inside an emulated environment. Okay, so this is actually just some simplistic example. There are more elaborate examples on time and anomaly which you could find in the paper if you're interested in them. Let's jump to the second example. So the networking example. This is actually a check that has been documented by a colleague called Jaunoka, who is using as an indication that we are inside an emulated environment a connection on localhost to port 445. This is the SMB port that is open on all professional Windows operating system. And in case the emulator fails to implement access to this port, then we are able to use it as an indicator that we are inside an emulated environment. Okay, so I'll jump to this third category, which is interaction with the file system. And here we try to implement several checks that will simply try to write and read to the file system, try to write and read to EFS streams, which is another feature of the Windows operating system file system. But we tried also to come up with checks that use EPA functions that rely on the file system. And this is an example of check that is using load library to load system DLLs and fake DLLs. If the system DLLs are not loading, then this is not a fully functional Windows operating system. And we are able to identify that we are inside an emulated environment. And in the same fashion, if the fake DLLs are loading, then this is definitely something fishy. And again, we are potentially inside an emulated environment. Okay, this is another very interesting example because it really shows the limitation of emulators. This is, by the way, a check that bypasses all emulator implementations. So what basically this check is doing is that it's using obscure EPA functions that have a specific behavior inside the real environment. And because the emulators are not implementing this logic, and because it's impossible for them to implement the logic of all EPA functions, otherwise it means re-implementing the Windows operating system, it's always kind of easy to always come up with some functions who have some specific behavior that is different inside the emulated environment and be able to bypass. I wouldn't expect it to work after we publish this. Well, I'll jump to the final category, which is binary instrumentation. And here, actually, a lot of the checks that we used are based on work that has been done by two researchers, which is Francisco Falcon and Nacho Riva, who basically come up with a lot of checks to detect dynamic binary instrumentations. Few of these checks are very specific to the Intel instrumentation framework. Others are very generic. And this is an example of check that is simply retrieving the parent processor name and comparing it with explorer.exe or cmd.exe, which should be the case of our malware. And if it's not, again, we are potentially inside an emulated environment. Okay. Well, here I'm going to show you just a demo of what really happens when we're using some of these checks. That was just the help menu. So what I'm doing is that I'm packing a Meterpreter bind shell using Notepad++. Meterpreter because it's interesting from a pen tester point of view. So I have two versions. In both versions, I'm using XOR encryption. Actually, encryption, whatever you use, have little impact on the detectability of the malware. We're using the resource packer to avoid any static analysis. And for the second sample, we're using an anti-emulation check called time4. And I'll be showing you what it is doing. Here, I'm simply generating my two samples and trying to verify. Okay. So here I'm going to be testing them against, inside the virtual machine against the Microsoft Security Essentials. Microsoft Security Essentials is a very interesting example because actually they have maybe the most robust emulator implementation, as you will see. Here I'm just simply updating it to make sure that it has nothing to do with signature and to show you it's really the use of a detection vector that is making it detectable. Okay, here I'm actually just decrypting my samples. I make sure that they are encrypted so that they won't get detected during transfer. I'm disconnecting it so that I make sure that my sample don't get leaked. I'm using my super lead password, and then I have the password, the two samples decrypted. And one initial thing that we see that once they get dropped, apparently there was some initial analysis that it didn't get, was able to detect them because it's basically using static analysis. And now that I'm doing real analysis, which will take more time, it's now able to detect the first sample. And basically because there is any anti-emulation check. So let's see what's really happening with the second one. Here I'm using a tool called EPA Monitor. This is a tool that allows us to hook functions, allow us to retrieve their different parameters and be able to monitor. Here I'm simply hooking the load library function because I know that this is what my anti-emulation check. And once I started executing it and hooked to it, what you will actually won't probably really see it is that you will see that there is a repeated call to a function load library with kernel32.dll. And it's actually repeating this call, I believe it will repeat it for 500 times. And what basically it is happening is that by repeating this function, it's simply simulating a big sleep. And this way it's delaying the unpacking. And this way it will trigger any timeout analysis and not be able to analyze it. Okay, so what does that mean is that using the resource packer, we're able to bypass static analysis. Using one of these anti-emulation, we're able to bypass emulation. And this is actually the result of the different checks. This is a table that dates back from August. We did the same checks 2 months before. Yes means it bypasses, no means it doesn't. And between the 2 checks that we performed, we have already seen some differences. The first one is that actually there are 2 interviruses that we did not identify as using any emulation, either because they simply was not implementing it, or because these samples that were created were not triggering the use of any emulation. And it's actually the case of EVG and ASET. Another thing that we could see is that actually Kaspersky is not able to identify 64-bit executables, which probably means that it's not implementing any emulation for 64-bit executables. However, we could see that it is very comparable to 32-bit executables of Microsoft, and even in some cases superior to Microsoft emulator, which is something that wouldn't be expecting, because Microsoft is emulating their own operating system. They have access to their own source code, which is not the case of Kaspersky. However, as you could see, there are actually several checks which are allowing us to completely bypass all the emulator implementations. Okay, well now what does that mean is that, as I said, using the resource packer, we're able to bypass static analysis. Using one of these checks, we're able to bypass code emulation. However, meaning we're able to bypass any initial analysis. The problem is, I'll show you a demo here. So it really doesn't look really well. But anyway, I have 2 machines, one with the Metasploit and a second machine which have EVG intervirus, okay? So here I have retrieved a interpreter shell on the other machine, meaning I bypassed the initial analysis and now it is running on the second machine. And here I'm simply checking the IP address, then I'm dropping a Ruby shell and executing a command that will try to migrate to explore.exe. What basically will happen, this will take a little bit more time, but trying to perform this action, this will trigger an antivirus alert. And the antivirus alert will not be able to say that this is Metasploit or it is Meterpreter shell. It will simply see that there is something suspicious. And here I'm going to show you in bigger. So here I'm simply trying to migrate to explore.exe, and here it is seeing that there is something suspicious. And this is what is commonly called as dynamic or heuristic analysis. So the same question applies again, is that how our antiviruses are implementing this detection method, and again, is it possible to bypass it, and hopefully bypass it in a generic way? Well, the problem with heuristic analysis compared to emulation is that there is no big consensus among antivirus vendors on techniques that are commonly used to implement. There are actually one that comes often, which is a hooking technique called SSDT hooking. What SSDT is, it is actually a dispatch table that exists on the kernel land that references functions that are accessible from the user land. And by performing SSDT hooking, the antivirus is able to log function calls with their different parameters in a way that it is impossible to bypass from user land perspective. And this is used in the way that if the antivirus sees that there is a certain process, that it is, for instance, calling function A, followed by function B, followed by function C, with certain parameters and certain options in certain order, it's possible to say, well, this is actually the signature for process hallowing, which is mostly used by malware authors, then it will flag it as suspicious. Well, SSDT hooking is just one of the many hooking techniques that exist. And there is particularly one hooking technique that we use to implement anti-heuristic methods. And this hooking technique is called inline hooking. And what inline hooking does is that, for instance, I'd like to hook certain function. Here, I'd like to hook create file A function. So what inline hooking will do is that it will disassemble this function. It will replace these initial opcodes with one that would allow us to jump to our newly allocated function, while making sure that it is correctly padded so that I won't impact the rest of the body of the function. Then it will save these instructions into a new memory region called the trampoline. This way, if I'd like to call the old function, I can call the trampoline, which will jump to the body of the function and be able to execute it. And here I'm just going to show you a demo of how this is happening. So I have an executable, which has been modified for demonstration purposes. It's spitting a lot of debug data and message boxes. And I'm using dbgview to be able to access this debug information to see what's really happening. Okay, so the hooking will happen on the create file A function. So this is the debug info on the create hole. This is actually the disassembly before, this is the disassembly after, and this is the trampoline. Okay, so now let's really look how it's really, if this is really how happening inside the debugger. So here I'm going to use an only dbg. I'll be executing because I know that the hooking only happens after the first message box. Here I'm attaching to the function. And then I'm looking for the create file A functions to see its disassembly, to see how it looks before the hooking will happen. And as you'll see, or you can see, that actually this is simply standard instructions, which actually instructions of the create file A function. Okay? So now we'll continue execution. meaning that after this message boxes, dehooking has started, and if we pause it and we look back to our function, we're able to see that this instruction has been modified, and it means that it has implemented hooking. Okay. Well, this is used to implement two evasion methods. The first one is a technique we call API translation. And the logic is that imagine you'd like to achieve persistence. You probably will do so by adding a certain registry key, meaning you will be using registry handling functions which might trigger a known signature. Well, instead of calling these functions that will trigger a known signature, API translation will replace these functions with a new one for which there is no known signature. And in this example, it is doing it by replacing this function with a system command that is calling the rig executable with the appropriate parameter that it has retrieved. What happened is that the intervars will see this coming from a different process. This process is signed by Microsoft, hence it has lower profile risk, and then it will no longer identify it. The second technique that we implemented is a technique we call API junk injection. And the logic is, because this detection method is expecting that there is certain function calls in certain order, API junk injection will hook these heuristically dangerous functions, and then it will inject functions that do not modify the logic of the application, but will modify this order. This way, it will no longer match that expected pattern. The problem, however, with this approach is that it has a significant performance impact. For every function, there is a lot of functions that are repeated. It is, however, generic when it comes to bypassing this sort of heuristic detection method, compared to the first one, which is API translation, which is less generic, because you'll need to come up with an API translation for every signature. And it's not always that easy, and in some cases, it's simply not possible. However, it has little or no performance impact on the application. Maybe you have some ideas on something that is both the generic and have no performance impact. If you have it, I'd definitely like to hear about it. Okay, so to rapidly summarize, what we have seen from our research is that there is an evolution of detection method, either by simply enhancing static analysis or by using more powerful techniques. It's, for instance, the case of code emulation, which is definitely a powerful technique. The problem is it's so complex to implement, and on the other side, it's relatively easy to always have some discrepancy between an emulated environment and a real environment that we could use to bypass it, that makes it, this technique has little, in my opinion, little success. The second thing, which is heuristic analysis, and here our experience with trying to implement generic bypasses, it's difficult to implement. However, heuristic analysis will only operate after the program has started execution, which is sometime a little bit too late. The final thing that we could mention is that there are some technologies that deserve to be explored to be able to enhance detection, malware detection, which is, for instance, the case of machine learning. There were actually some patents that mentioned neural networks. I'm not sure if there is any real implementation using it, but it's definitely something that deserves to be explored. The last thing, which is cloud-based antiviruses, which have less issues to deal with. It's, for instance, the case they have no performance impact. They don't need to use emulator. They could use sandboxes, even if sandboxes have their own bypasses. But it's something that allows us to deal with some of the limitations on desktop antiviruses. Okay. Well, I hope that it was clear. I don't know if you have any questions. Otherwise, thanks for listening.